Hey everyone, in today's tutorial I want to go over a project from the Starkware Exploration team, which is a Rust implementation of a Merkle Sum Sparse Merkle tree. Now the unique advantage of these trees is that you can build what's called a proof of liability, which you need in order to increase the transparency and also the security of the Cashu protocol. So very briefly in this tutorial you're going to learn about Cashu, you're going to learn about proof of liabilities and how those are built using the Rust implementation of the Merkle Sum Sparse Merkle tree. And then specifically, I also want to tell you about the sum aspect of the tree and also the sparse aspect, and then how you build the tree and what you insert into the leaves in order to receive the root of that tree. And so we'll do that by diving into the code, and I'll show you which parts you need in order to build your proof of liability. So before I do that, an overview of Cashu. It's this electronic Ecash payment system, which is private, it's simple. This is how it works. So let's say that you have user A and then you have user B. User A is going to deposit their Bitcoin or their Satoshis into what's called a mint node. This mint node is running Lightning nodes, and in exchange, the node is going to issue what's called Ecash token. And then the user can send that Ecash token to another user. And if user B decides to redeem that Bitcoin, well, they can go to the mint node and they can burn that Ecash token and in exchange get the Bitcoin. Cashu is also private. What is this privacy component in the protocol? So the reason why Cashu is private is because it uses a blind signature. So this is a cryptographic primitive that has been around for many decades, but it's integrated here in the Cashu protocol. The mint node is never going to actually see the unblinded secret that becomes the token. So how a blinded signature works is that first a user is going to generate a secret and it's going to encrypt it. So it's going to blind it. And then this secret is being sent over to the mint node, and the mint node has no access to the actual secret. So the mint node signs this value, and then we have a blinded signature of something that the node has never seen. The combination of the secret and the blinded signature is the representation of the token. This right here is the token. And whenever the mint node comes across some other tokens, it's going to check the signature and it's going to be able to say, hey, yeah, this is actually worth something. So the blinded signature actually acts as a promise. The mint node, what it does, it sends it back to the user, and the user can decrypt the blinded signature, but it's essentially the combination of the secret and then the signature which represents the token. I'll show you the need for the blinded signatures and also the need for the secret whenever you want to create the Merkle Sum Sparse Merkle tree, and also where it falls whenever we're creating this proof of liability. The mint node right here is the one running the Lightning infrastructure, and user A and user B are going to use Cashu wallets. So they don't hold the custody of their Bitcoin. It's the mint node that does, and this requires a trust assumption. And so the users have to trust that the mint node is not going to either do what's called a fast rug or a slow rug. Fast rug would be in the case where the mint node can just switch off the node and run away with the funds. And then a slow rug would be the mint node inflating the supply of Ecash without having any backed Bitcoin. So it indebts itself to the users slowly and progressively without users actually noticing. To solve this slow rug, we need to implement proof of liability. So we need to find a way to prove that the mint node has not been secretly issuing any additional unbacked Ecash. And next to already proving the reserve, so that's something that you see in centralized exchanges, they prove that they have a certain amount. So that's the POR. Next to the mint node submitting a POR, it should also issue a proof of liability. So next to claiming that, hey, I have this amount of Bitcoin, it must also claim, hey, I don't have any outstanding liabilities, or I don't have issued Ecash that is not backed by Bitcoin. Without the proof of liability, but with the proof of reserve, the mint node could very well claim that, hey, I have this amount, but in the background it lies and it's been issuing additional Ecash. Let's say that we have a mint node that has been claiming, hey, I have 10 BTC. Then it has the equivalent worth in Ecash. But let's say that you're dealing with a dishonest mint node. So the mint node claims that it has 10 BTC. So it says we have 10 BTC, but we increased our reserve to 10 BTC. So we had to issue more Ecash progressively. So this size goes here. But now you see that it's not equal. So this node is not being honest. And it's inflating the supply of Ecash. And there's no actually backed Bitcoin for that additional Ecash. And so the users will actually realize this slowly because they have the equivalent in Ecash, but then when they go back to the node and they ask, hey, I want my Bitcoin back, it's not actually backed by any additional Bitcoin. This is the moment that the user realizes that there's actually no backed Bitcoin for the Ecash that they had. So how do you actually create the proof of liability? With every minting and with every burning of the token, you create a list. So you create burn proofs, you create mint proofs. The burn proofs, we're going to call them melts. So you're melting the token, and then you're going to also mint the token. So you're going to have mints and melts. The ultimate goal is for users to see that mints and melts are included in the mint node's data structure. So we have to find a way to structure the mint list and the melt list in a way that it becomes easy to create a proof of liabilities. And so the way that we structure this data set is through a Merkle Sum Sparse Merkle tree. We're going to have two trees, one tree that represents the list of the mints, and then another tree that represents the list of the melts. This type of data structure combines two unique properties, so this sum property and also the sparse property. Just as a refresher, this is a classic Merkle tree. You're going to have the leaves, and the leaves are hashed together until you get the root of the tree. And the root is this cryptographic commitment for all of the data. Then you have the sparse component, essentially means that you can leave some leaves empty in the tree. And then you have the sum aspect of the tree. So the tree's root is going to represent the sum of all of the leaves that get accumulated together in all the parent nodes until you get the root of the tree. And we use the sparse component because when crafting your mint tree or your melt tree, you're likely never going to fill all the leaves, given that the list of the melts and then the list of the mints can vary. And so through this data structure and through the proof of liability, you want users to be able to verify the inclusion of the mint and the melts in the tree. So now let's actually look at how the Merkle Sum Sparse Merkle tree is being built. If we look at the proof of liabilities function, one of the first components is that it looks at the key sets. In the Cashu protocol, we have what's called rotating key sets. So the keys that are used to sign the issuance of new tokens, they rotate every epoch. So for instance, every month or every 2 months. And this is a security aspect from the Cashu protocol. So whenever we create our proof of liability, we say, hey, for this particular key set, let's build this particular tree. So for each key set, the mint node is going to publish a record of all the mints and all the melts, given that epoch. To build the Merkle Sum Sparse Merkle tree, we get all the key sets that ever existed in the mint node, and we build the tree for each particular key set. It's also worth noting that in the Cashu protocol, the epoch isn't 1 month, so it depends. But if you set it to 1 month, or if you even set it to much shorter time frames, you actually lose in privacy because it becomes way easier for external parties to analyze the transfers. And then we create a vector where after we create the mint trees and the melt trees, we send those to that vector, and that is being sent over to the client, so over to the user, so that they can have access to those records. We create two mutable variables, so the mint tree store and the melt tree store, which helps us track the data but also access the data about the tokens that have been minted and also the tokens that have been burned, so the melts. Afterwards, for each key set, we create a namespace in the database to store every mint and melt tree. So for example, if we have a mint tree for the key set 123, it is going to be stored in the namespace mint_123. And so whenever we query the node, we only retrieve the data that is relevant to that specific key set's mint or melt tree. So here we're doing it for the mint tree. This is where we're actually going to insert the leaves into our Merkle Sum Sparse Merkle tree. So this is for the mint, and then here this is for the melt. So let's say that we want to do it for the mint tree. If we look in the function getMintTree, this line right over here takes care of creating the Merkle Sum Sparse Merkle tree and connecting it to the database, and then doing that while allowing us to perform tree operations. So that, for instance, is inserting a new leaf, all while maintaining the persistent state of the tree. And then particularly for the mint tree, we're going to tap into the database and we're going to check if the leaf has an insertion or if it's empty, and if it is empty, then we're going to actually insert the leaf inside of the mint tree. And then we do the same for the melt tree. So right here we have our getMeltTree function. Again, we're creating the Merkle Sum Sparse Merkle tree, and we're doing a check where we see if we can insert a new leaf, and if we can, then we will insert the new leaf in the tree. One of the last parts is the actual building of the tree leaves. So for instance, for a mint tree, it takes the blinded signature, and remember, the blind signature is this attestation from the mint node that it issued the token. So it's a recognition that it issued the token, and we use that to create the key and the value. So the key is the SHA-256 hash of the blinded signature in the bytes format, and then you also have the value. So that is the blinded signature in bytes. And then you also have a third component of the tree. That's where we tap into the sum component of the tree. This represents the actual value of the mints. Let's get an example actually of storing 100 Ecash. So if the mint issues 100 Ecash, the way it's going to insert that data in the Merkle Sum Sparse Merkle tree, it's going to split it in 2, 32, and 64, because Cashu works with powers of 2. And then the sum, so the root, will represent the cumulative sum of all of the nodes. So that's the sum aspect of the Merkle Sum Sparse Merkle tree. And then the sparse component is that we're not filling in all the leaves. So after building the trees, we get the mint tree root and the melt tree root, and we push those into a struct, so the Proof of Liabilities struct. The user can now check whether the mint is creating a new token without any backing, if it's failing to record any spent tokens, and if its outstanding liabilities is superior than its Bitcoin reserves. Now is the final part of the tutorial, and it's actually running some integration tests where we're going to see if, given the Merkle Sum Sparse Merkle trees that we're building, we can generate and verify the Merkle trees, and so get a proof of liability. The goal of the test is to verify whether these mints and these melts are included. This test is going to run a Bitcoin testing environment and also a Lightning testing environment. It's also going to set mints and melts and then verify the proof of liabilities for both of the mints and the melts. So here we have our first test that ran okay. We begin verifying the Merkle proof. Afterwards, we verify that the token that was issued by the mint is indeed included in the mint's tree root. Here we have a hexadecimal value, which is actually the blinded signature from the mint. And so we see if that one is included in the mint's tree root. Afterwards, the system retrieves the Merkle proof and it verifies it against the mint's tree root. And if the verification is successful, we have a proof verified notification. And in the test, we also do this for 2 other mints and then also a melt. And that's it. So in this tutorial, I got to show you how you construct a Merkle Sum Sparse Merkle tree. So it's an implementation done by the exploration team at Starkware, and how we need those in order to create proof of liabilities, and then how those benefit the Cashu protocol. So with this new type of data structure, the Cashu protocol next to its proof of reserve can create also a proof of liability. And so this would increase transparency and also the security of the protocol. And so it reduces the risk of a mint node conducting a slow rug. And I hope you enjoyed this tutorial, and I'll see you in the next video.